So we're in the chapter on thermodynamic properties, and we covered quite a bit. I spent probably more time than a lot of instructors on the PVT surface. So that's a 3D graphical representation of data coming from experimental observations or measurements on the relationship between pressure, specific volume, and temperature. Often we show that for water. We can show it for different refrigerants. Conceptually, I think it's a good introduction to properties. So this was the surface, the PVT surface. I emphasized the axes: temperature, hot; volume, larger; pressure, higher. Emphasized the single-phase regions, something like a solid region, liquid region, vapor region, and then the separation out here is in the supercritical region. It's not clear, but there is a clear distinction between the solid and the liquid region. And then we had two-phase regions. So the one that we spend a lot of time in is right here under this dome. We call that the dome, going from the critical point down. This is where you have liquid and vapor in a equilibrium mixture of liquid and vapor. Then we also had another two-phase region, solid liquid, and then we also had solid vapor. Well, if we have single phase, we have two-phase, maybe we have a three-phase region, and there is a three-phase region. The three-phase region is this line, that line going right in there. And so it can go all the way to vapor. That you could have liquid, you could have solid, you could have a mixture of the three, and in equilibrium. But it only happens at a unique pressure and a unique temperature, the triple point temperature and the triple point pressure. So that's the triple line in 3D. I think I spent some time showing this illustration. We just showed this illustration. What is the difference between these two? It's just a verbal question. Can you see the difference between them? Yeah. So what happens is, as you're, let's say, going from a solid to a liquid, let's say you're at this pressure right here, and you're in the solid region, and you're going to go to a liquid. How are you going to do that? You're going to heat it up. The temperature is going to increase at constant pressure. And so you're going along at a constant height along that solid face, and you're increasing temperature, and then you hit this point where it's saturated solid, and then some of it starts to turn into liquid. And which way does the specific volume go? Does it increase? My two hands, increase or decrease? It decreases. So the mass is going to occupy a smaller volume in the liquid phase. True? For this case. That's kind of weird. That's very abnormal. That's water. This is H2O. It's a very common fluid, but it has very unique behavior. And that's one of the characteristics. Where more commonly, if we're same pressure, low temperature, we're in the solid phase, we heat it up, constant pressure, we start to get the saturated solid, then we're going to start generating some liquid. What does the specific volume do? It increases, so the same mass occupies a greater volume in the liquid phase than it did in the solid phase. So it's increasing. There, that's very common when you melt. Liquid is larger specific volume. Now, we have projections of these surfaces so that we can put it on a 2D plot. Engineers like 2D plots. A lot of people like 2D plots. We don't like 3D representations. They're really hard to read at times. But a lot of that information can be projected. So we can look at, this is like a cube, and you look down or up, front, back, sideways. And there you go.
Thank you.
You're welcome. I shouldn't distract you, should I, by chatting? Let you get your stuff. So we could look at a projection from this direction, or this direction. 3 directions, really. Okay, so the same is true for either one of these diagrams. But if I wanted, let's call this projection A, projection B, or projection C. All right, if I wanted to look at a P T diagram, which projection would I look at? This is the first clicker question. And let's see how we did. And you're absolutely all correct. The answer A is the correct answer, isn't it? It's so when we look at that projection, what's on the x-axis? Temperature. What's on the y-axis? Pressure. Pressure. Let's say I looked at projection B. What would projection B give me? It would give me the pressure volume diagram. This gives the pressure temperature diagram. And what about projection C? It would be what? Temperature volume. Yeah, temperature specific volume. Now, it's a little hard to see, but if I look at the PT projection, okay, looking that way from A perspective, what does the triple line look like? It looks like the triple point. And so you'll see the triple point called the triple line and the triple line called the triple point, because we don't spend that much time looking at the 3D surface. And so it'll look like a point. Let's take a look at this projection. So when you project it, that point is the TP, the triple point. Okay? What is the triple point? You could have three phases coexisting in equilibrium. You could have all three phases there. That's why it's triple. Solid, liquid, vapor. All right. Then you take a look at going out to the critical point. Out to the critical point. What is all that? That's all of the two-phase liquid-vapor mixture region that's under the dome. You could have in equilibrium, some liquid, some vapor in equilibrium. Okay. What about going from the triple point in lower temperature, lower pressure? That's this surface right in here, this solid vapor. This is two-phase solid vapor in equilibrium. And then going up right through here, that would be the solid liquid in equilibrium. The two-phase, two-phase, two-phase. So the two-phase regions on a pressure temperature diagram, a PT diagram, are lines. They're lines. And what anchors it? The triple point right in the middle, right there. And then scooting up is to the critical point. Then this way, with no point in end, it just continues on, is that solid liquid interface, and then the solid vapor. You know, I'll ask students in Thermo 2, hey, I'll put up a pressure temperature diagram, and I'll kind of sketch it like this, and I'll say, hey, what was the name of that point? Half of them critical point, half of them triple point. So it really helps if you know this. And I did check my chemistry book, and this is in the chemistry book that I'm sure that you used for your chemistry class. So it's a good review. Triple point, critical point, and then I'll say, what is this region out here? Is that which phase? Which phase is out here in this region? And that's the liquid. And then out here, solid, and then out here, the vapor. Right, right. Okay. Now this brings up an interesting point, is that if I'm at, let's say, 1 atm pressure, that's 101 kilopascal, that's 14.7 psi, whatever pressure, but it's 1 atmosphere pressure. It's the air pressure in this room, right? And I heat up a pot of water, liquid water. It starts liquid maybe at this temperature right here. So it's definitely liquid. I heat it up, I heat it up, I heat it up. Can you see what's happening? And then it gets out to this point. What's going to happen when it gets to that point? The pot of water is going to start to boil. And as I continue to add heat, it'll boil and more of it go into the vapor phase until it's all gone, it's all boiled, it's all vapor, it's expanded out into the room. What is that temperature? 100 degrees C. Let's say I put it with a pressure cooker, and somehow I was able to modify that pressure such that it was always 2 atm. I start at the same temperature, it's liquid, I heat it up, heat it up, heat it up. Does it boil at 100 degrees C? It boils at a higher temperature. Higher temperature. And so this line right in here gives us a couple different ways to look at it. If you give me the pressure, I give you the temperature. So you could get the saturation temperature as a function of pressure, or look at it this way, go from give me a temperature and I'll give you a pressure. So the saturation pressure is a function of the temperature. But that temperature for this two-phase liquid vapor boiling condensation has to be between this temperature and that temperature. What is that temperature? The triple point. What is this? The critical point temperature. We'll get numeric values for that, but for water, because we spend so much time with water, the triple point temperature is around 0 degrees C. And the critical point temperature is around 370 something degrees C. Okay? So that's quite a range of temperatures, as well as low pressure to pretty high pressure. All right. So we talked about the single phase regions, the saturation temperature, the saturation pressure. What's the saturation temperature? Give me the pressure at which it's going to be changing phase, and I'll give you that temperature, that saturation temperature. There's one and only one saturation temperature for given pressure. If I say it's at 1 atm, somebody says, well, tomorrow it may boil at 110 degrees, not 100. That's not true. It's going to boil at 100. It's only one saturation temperature for the given pressure. Okay. Likewise, there's only one. So in this two-phase region, guess what? My favorite two properties that we like to be independent, they're not independent in that region. They're not independent. Temperature and pressure are not independent in the two-phase region when you're undergoing phase change like that. The biggest one is going from liquid to vapor. Okay, we got the critical point and the triple point. Now let's take a look at the other projection that's very popular, looking this way. We pick up the pressure specific volume diagram, pressure specific volume. Now the first rendition, they're trying to put a lot of information on here. There's that critical point, here's that triple line, even the solid region kind of backing in there. But a lot of times we just look at liquid, vapor on the PV diagram because the solid is so hard to see it. Okay, so we just throw that off. And then what do we have? Now we see the shape of the dome. The dome is shaped like this. And so underneath the dome in this shaded region is the liquid vapor two-phase mixture. So I could have a two-phase mixture at this specific volume and that pressure. I could have at the same pressure maybe a higher specific volume. What changed? Let me ask this question. Did the temperature change between point A and point B? Did the temperature change? No, because the pressure didn't change, and temperature is not independent from pressure in the two-phase region. So they had the same saturation temperature. What changed? The volume changed. Well, that just meant more of it is in the vapor phase than in the liquid phase. It's occupying a greater volume. B occupies a greater volume than A. So for the same 1 kilogram, I'll have maybe 90% of it in the vapor phase and only 10% of it in the liquid phase. Something like that. All right? Now, a lot of times we show on the pressure volume PV diagram lines of constant temperature. Can you see the line of constant temperature? Here's a line of constant temperature right here. there's a line at constant temperature. You know, that temperature is quite high. That temperature is above the critical point temperature. What did I say the critical point temperature was roughly for water? Yeah, 370 some. Okay, so that's really hot. Okay, now let's say I do the isotherm where it's really the critical point temperature. That's a line at constant temperature. It comes up and it goes right through that critical point, has a little inflection like that, and then scoots up. How do we know that? Experimental data. How about if I grab one that's less than the critical point temperature? Well, it's going to come up, it's going to hit the saturated vapor, it's going to go flat straight across because it's not independent of pressure in the two-phase region, and then it's going to scoot up. So those are lines of constant temperature on a PV diagram. Okay. The triple line looks like a point on what projection of the PVT surface? On the PV projection, the PT projection, or the TV projection? Yeah, we got a clicker going. So I didn't say I asked hard questions, but it makes you think, doesn't it? It makes you think. And all right, well, let's take a look at our results. So the triple line looks like a point when you're looking this direction, which gives us the pressure temperature, the PT projection, which is answer B. Right? Isn't that correct? Yeah. And it doesn't look like a point when you look this way. When you look at the PV diagram, it actually is more of a line. And if you look down that way, which gives you the temperature volume, it's a line too. But often we don't plot that low a temperature or low of pressure when we're interested in boiling and condensing water. We're usually above that critical point temperature and pressure. Not critical point, triple point temperature and pressure. So for water, this is the way we typically show the temperature volume diagram, the TV diagram. We just show the two-phase region, the dome. We try not to show the solid liquid region, two-phase region. We typically stay, maybe the lowest temperature is around 20 degrees C. The temperature for the triple point is 0.01 degrees C. So we stay well above it on the plot. So we don't even show the triple line. And here is all in this region, it's liquid. And then all of this region, it's vapor. This is the critical point at the top of the dome. And so this is the supercritical fluid region. It behaves a lot like vapor over here and a lot like liquid over here. But if you're a purist, it's really difficult to say, you know, where's the demarcation between liquid and vapor behavior. It's like a mushy cloud. Actually, you could see some YouTube videos if you go out and look. Somebody will experimentally show you what it looks like. It'll show you it through a window. Oh, look at that. I can see some water clearly in liquid phase and vapor above it. Now let's change the pressure and temperature of this and see what it looks like. All right. All right. Now, so let's do some thought experiments. We'll start off with water at 20 degrees C, and we'll start it off at 1 atmosphere. That's about 1 atmospheric pressure of 1.014 bar, or 14.7 psi. True? So if you heat it up, it's going to expand a little bit until it hit this point F. That point F is where it is saturated liquid, meaning that if I dump a little more heat into it, it's not going to increase temperature anymore. It went from 20 all the way up to 100 degrees C, so while I was heating it up, while it was in the liquid phase, it was increasing temperature. But now that it's hit its saturated liquid, if I dump some more heat in, it'll stay at 100, but I'll be getting more and more vapor. More and more vapor, more and more vapor, more and more vapor, until it gets out to point G. G is saturated vapor. Now it's all vapor. If I heat it up any more, it'll continue to expand. Now the temperature will continue to rise. For a long time, it stayed at 100 during that constant pressure, boiling or vaporization, that phase change. Okay, and then as you continue to heat it up, it goes out in this region. Here, it's the vapor region. A lot of times we call that the superheated vapor. It's heated above the saturation state. Okay, is this a line of constant pressure? This whole line of constant pressure? That's right. That's a line of constant pressure. And the easiest one to understand is the pressure we have a lot of experience with, and that's atmospheric pressure. All right. Why do they use F and G? Well, if you were the first to say, I need a subscript because I want to know what this V sub is at when it starts to boil, when it's a saturated liquid, a lot of us would have put V sub L for V sub liquid. Right? That's what I would have picked. That's probably what you would have picked. But for many years, journals and other places have avoided the subscript L. Why would they avoid the subscript L? Because it's easily confused with the subscript number 1. And so journals and publishers, and for many years, now this was especially before we got all our fonts, you know. Now you have so many choices in fonts, you could make that L look very distinctive and clearly not a 1. But there were a lot where, no, it would be so easily confused. So what they did was, a lot of thermodynamics was done in Europe, in Germany, and the German word for liquid starts with the letter F, and so that was already into a lot of the thermodynamic literature, and so that's stuck. You might say, well, is that like for fluid? Well, English fluid, yeah, but there's a German word that's F for liquid, and I forget the word. Okay? Anybody know German? Well, there you go. And the same thing for G. You say, why don't they put V sub V? A little confusing. So V sub G is for saturated vapor. So V sub F and V sub G. You just have to say, okay, I can understand the historical context. This linked back to some German words, and a lot of the thermodynamics was done over there, and so there you go. That's why we still use it, and it avoids confusion. Okay, what happens if I boost the pressure to 10 megapascal? I start at 20 degrees C. Well, I'll heat it. It'll go to a lot hotter before. It'll get much above 100 degrees C. Maybe it gets up to, I should look this up, what does it get up to for 10 megapascal? Let me see if I could find that. Got to flip open the book. Okay. Can't read. About 311 degrees C. That's quite hot. But when it gets to 311, guess what? That's the saturated vapor state for that pressure of 10 megapascal. So that's V sub F. And then it starts changing phase. And then it's V sub G, saturated vapor. And then if I continue to hold it at 10 megapascal and heat it up, it gets higher temperature. Well, then you could start at 20 degrees C with something like 30 megapascal, which is above the 22 megapascal critical point pressure. And there, you just heat it up. It doesn't go through a distinct phase change. It sort of just blends over. There's a region where it more rapidly increases specific volume as you're heating it up, but it's not held at a constant temperature as you're heating it up while it changes phase. All right. Take a look. At lower pressure, lower temperature, there's a dramatic change between V sub G. It's much greater than V sub F, isn't it? How about at a higher pressure? How about when I get right up almost, let's say not 22.09, let's do 21.5 megapascal. If I do 21.5 megapascal, what's going to be the difference between the value of V sub G and V sub F? V sub G, F and V sub G. It's going to get closer and closer together. And so at the critical point, they're the same. V sub G and V sub F are the same. So you really just slowly lose that distinction of the expansion. Okay. So let's talk a little bit about what happens in between. So in between, we still want to have a specific volume of the mixture. It could be maybe right here, or maybe right here, or maybe right here. Let's talk a little bit. If the specific volume of the mixture is real close to V sub F, does that mean it's all liquid or all vapor? It's all liquid. If the V is very close to V sub G, it's all vapor. All right. For this case right here, can you just sort of eyeball it and tell me, well, I think it's mostly liquid or mostly vapor? Mostly vapor. And if I said visually it's going to be a fraction based on the lengths of lines, what percent would be vapor for this case right here? Just visually. 90%. 90% vapor, 10% liquid. Now you ask, this is always the killer. When we're in thermodynamics, when you're talking fractions of a mixture that are liquid and vapor, are you talking volume fraction or mass fraction? Let me just say right here now, mass fraction. And we'll emphasize that again. This is typically an exam question on the FE exam. They can weave that into a question on, after you pass all thermodynamics, you're trying to become a registered engineer, professional registration process. You have to pass the FE exam, and probably, I don't know, I've seen a lot of study guides, and this type of question will be on there. And there's a couple other questions I'll point to, and I'll say, you know what, this is going to be on the FE exam, high probability. I can't guarantee it, I don't write the exam, but it's high probability. And they'll ask a question that penetrates down to, does a student know the difference between, is it a mass fraction or a volume fraction? Okay. So right away, I'm going to tell you it's a mass fraction. Okay. So this would be 90% by mass, that's vapor, and 10% by mass. What about right here? 50-50, right? 50-50. Well, let's go ahead and think about what is the specific volume of my mixture. Is it the total volume of the mixture divided by the mass of the mixture? Is that the definition of the specific volume? And that volume, I need to kind of maybe build it with a little piston cylinder. Here's a cylinder, and here's a piston in it. And I put the piston, and that piston has weights, and it seals the system. And I'm going to begin with a little bit of liquid trapped in there. And then I'm going to heat it up. Okay. As I heat it up, it starts to change phase. And I don't know if I can draw another. Let me try and do that. Duplicate this. Edit. Copy. Edit. Oh, paste. And I'll try and draw it right here. Later, that piston has moved, and because it's been heated up, and what do we have is we have the pistons moved way up here, and we still have a little bit of liquid in there, but it's less liquid. And then above it we have vapor, and it's liquid at the bottom. Okay. So what's happened is the volume is dramatically increased. But the total volume is the sum of the volume occupied by the vapor and the volume occupied by the liquid, true? And this mass is the total mass. It's the sum of the two masses. It's the mass that's in the liquid state. So the way you could write this specific volume is put it like this. The volume of the vapor divided by the mass, kick that over. And then I'm going to add the volume of the liquid and kick that over divided by the mass. Can you see what I'm setting up? Then I'm going to say, what was our definition of this V sub G right here? V sub G. Was it the volume occupied by the vapor divided by the total mass when all the mass is in the vapor state? It is. So if you do this, put the mass that's in the vapor state in the mass that's in the vapor state. I think I've handled mathematical integrity. It looks good. And then I go over to V sub F. V sub F is the volume occupied when it's saturated liquid divided by the mass that's all liquid. Well, put mass liquid right here and the mass liquid right there. And so what we have is we have V sub G times something plus V sub F times something. Now you could see why we deal with mass fractions, because this mass of the vapor divided by the total mass of the mixture, which is the sum of the mass of the liquid and mass of the vapor, that's going to be some quality, X. Quality is defined to be the mass of the vapor divided by the total mass of the mixture. All right. Well, then what is 1 minus the quality? Isn't that going to be, if the quality is 30%, then 70% is 1 minus the quality. And that would be the mass of the liquid divided by the mass total. Mass of liquid divided by the mass total. So this becomes 1 minus the quality. So when I'm interested in computing the specific volume of property in the two-phase mixture region, I need to know the V sub G, the V sub F from experimental data, and the quality. And then it's just basically a weighted average going between V sub G and V sub F, or V sub F and V sub G. Okay, let me scroll down a little bit. So the basic equation that you should remember is V sub G times quality plus V sub F times 1 minus quality, or rearranging, it's V sub F plus V sub G times, minus V sub F times X. Did I do the algebra correct? Yeah. And we'll see that similar format for internal energy and enthalpy and entropy in the two-phase region, as well as specific volume. What is this X again? Quality. What's it defined as? A volume fraction or a mass fraction? Mass fraction. And it's the mass in the vapor state divided by the total mass in the two-phase mixture, the liquid vapor mixture. So I really covered this already. The V sub F, that's the saturated liquid specific volume. If it's purely liquid, saturated liquid, then it's the volume of the liquid divided by the mass of liquid. True? Here's a number for you. If I have water at 1 atmosphere, it likes to boil at 100 degrees C. V sub F, 0.0010435 meter cubed per kilogram. That looks like a small number, but then we remember 1,000 liters in a meter cubed. So basically this is 1.04 liter per kilogram. Hey, that's what we talked about before. You show me a water bottle of 1 liter, and I'll show you a mass of about 1 kilogram. Full of water right there, right? So that's about 1 liter. Okay. Then we go, and V sub G is the volume occupied by saturated vapor divided by the mass of the vapor. And for water at that same pressure, V sub G is 1.673 meter cubed per kilogram. Now, who can show me between two hands what a meter length looks like? Who's pretty good at that? Are you pretty good at that? Who else is pretty good at it? You're pretty good at it? Okay, so now take it one by one by one. Now you have a cubic meter. See the size of it? But we have 1.6 cubic meters. So it's a little bit more, right? All right. Take your 1 liter water bottle that you've seen plenty of. A lot of you have drunk a lot of them, you know, you drink. And now think about that volume expanding. And now you have the notion of how much it expands. When you boil the water, it expands by a factor of 1/1600 times greater increase in volume. You knew that intuitively, but here is hopefully something that you can wrap your mind around and help remember. So water greatly expands when it boils at 1 atm. Now, if it boils at a much higher pressure, it has less of an expansion. If it gets all the way up to the critical point pressure, just a little bit below it, it really doesn't expand much at all, right? As it boils. But down there at 100 degrees C, 1 atm pressure, there's a significant expansion, almost a factor of 2,000. Then we wanted to calculate that specific volume in the mixture, V sub F plus V sub G minus V sub F times the quality is one equation to use. And again, what is that quality? Quality is the mass in liquid or vapor? Vapor divided by the mass liquid plus mass vapor in the two-phase mixture. It's a mass fraction. Okay, did I mess this up? This is V sub F. This is V sub F. Makes sense? Very good. You got that down, you go a long way because you just repeat it for internal energy, enthalpy, and entropy. Internal energy, what is it? It's due to the temperature and pressure. Mostly think about a function of temperature. It's tabulated, it's measured for us, it's put into tables, we can go get it. Okay? So we can put it on a per unit mass basis, lowercase u, which is cap u divided by the mass. But to get it, you probably need to either use the tables, or we'll talk about specific heats, like C sub V, C sub P. Let's say specific heats. All right. Enthalpy. Well, enthalpy, cap H, is defined as U plus PV. When a mathematician defines something, he usually puts 3 strokes in the equal sign. True? Are you familiar with that mathematical notation? 3 strokes. Hey, that's a definition. That's not equal. That's saying, hey, this is defined as. So let's take a look. This cap U, internal energy, that's P and that's V. Does this make sense? Does it have the same units? Typically, this would be something like kilojoules. Pressure, kilopascal. Volume, meter cubed. Are the units going to work? Sure, we recall that a kilopascal times a meter cubed is precisely a kilojoule in units, unit conversion. So yes, this does work for units. Now this is a property, this is a property, this is a property. It looks like all you did was do a little name call and you introduced a new property. Sometimes that's useful in engineering, sometimes it's not. It's useful. Okay, so there's another property. It's very similar to U, but it's called H, it's enthalpy. It's defined as U plus PV. When PV is real small, it's real close in magnitude to U, but sometimes PV is quite large. Lowercase h is cap H divided by M. What are the units on lowercase u? Kilojoules per kilogram. What are the units on lowercase h? Specific enthalpy, kilojoules per kilogram. Can you have 2 properties have the same units? Sure, here's a good example. Different meaning, u and h are not the same. They're similar, but they have exactly the same units. So you can't use units to distinguish sometimes and find an error in your work. Sometimes units help you identify an error, sometimes they can't. It's impossible. We need to figure out how to go get those values out of tables. Now, this is one of the things that people may or may not like about thermodynamics. Tables, tables, tables. Guess what? Just get used to it and get into the tables and master the tables. How many tables do you think there are in this textbook? I truncated the list right here. Now, thankfully, there's one or two that we don't get to. I don't ever go teach out of table A26, standard molar chemical exergy. Just even teaching both classes, I never get there. Although I get to table A27. I definitely do. Okay? So there's most of these tables you become very familiar with. Let's take a look at table A1. What's in table A1? Just take a look at what's the title. It's atomic or molecular weights and critical properties of selected elements and compounds. Here's that interesting term, molecular weights, that old terminology. What would I rather call it? Molecular mass, molecular masses. Okay. Then, before I jump into them, let's look at the structure. A, all the way through this group of tables right here, they all deal with water, 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 water. It's a very common fluid. We need to know how to use it. So this is the saturation table for water in the two-phase region, the liquid vapor region, where temperature is the primary input. The other one is pressure is the input. It's always confusing the students. It's like, why do I use table A3 sometimes? Why do I use table A2 sometimes? Do I know temperature and want other things? Use table A2. Do I know pressure and want other things? Use table A3. It's what's the easiest input. Temperature or pressure is the easiest input. Now, superheated water vapor. That's out in the superheated region or the vapor region. Compressed liquid. That's in the liquid region. And then we have one other two-phase region where it's solid vapor, water. So it's basically that solid vapor region. It's sublimation. All right. Then let's take a look at another group of tables. Refrigerant 22, refrigerant 22, refrigerant 22. Notice how many tables did we have for water? How many for refrigerant? Fewer. Water we have more information on that we put into the textbook or the authors chose to, so help students get the information easily. Refrigerant, you could have put the 5 tables in, but you usually don't want refrigerant 22 to be in the solid phase. You don't want it. You don't use it that way. So 3 tables is sufficient. Then another refrigerant, 3 tables. Then you go to another refrigerant. You got the picture. 3 tables, okay? A lot of times the refrigerants, they're boiling and condensing, and then they're superheating. There you go. Let's take a look at that first table. So here, what is cap M? Molar mass or molecular weight. Old terminology. Okay. A lot of times, earlier versions, they didn't even put the units in. They just left it like that. Cap M is 17.03 for ammonia. I loved it. I asked students, is M dimensionless? Oh yeah, look at the table. It's dimensionless. No, no, no. You have to be smart and know what it is. You have to know it's grams per mole or kilograms per kilomole or pounds per pound mole, but that's what it is. So the units are, they've added them since a couple editions ago, and it's kilograms per kilomole. Here's the chemical formula. Notice that they put air in there. Well, there's not one single, it's a mixture of oxygen and nitrogen, but they do have it, and we will treat it often as a pure substance with a molar mass of 28.97. A critical temperature and a critical pressure. I know there's not one single value there, but you have to approximate, and there you go. Argon, etc., benzene, butane, carbon. Now, let's take a look here. Why did they put that? Well, carbon is not typically in a gas state. It's like a solid carbon, so forget it. But the other ones, if they're in a gas state, they give us the critical point temperature and the critical point pressure. So for argon, it's very, very cold and high pressure. And then this is a Z critical later. That's the compressibility factor at the critical point, which is not close to 1, and it's around 0.2 something for many gases. That's table A1. Let's take a look at table A2. Table A2 is for water, and it's our liquid vapor temperature input. So, as this column right here is our temperatures. What does it go from? What's the lowest temperature in the table? 0.01 degrees C. What is special about that? Triple point. It's our triple point. What is the 100 degrees C? Boiling point at 1 atm. What is 374.14 degrees C? Critical point. It spans that whole range. They give you then, if I wanted to find Psat for the temperature, right there it is, this column. So the saturation pressure at 10 degrees C is this many bar. If it's at 360 degrees C, it's that many bar. That's the saturation pressure. Then I have two columns for specific volume, true? I have the saturated liquid and the saturated vapor. This always throws students a little bit for a loop, this 10 to the 3 right here. Okay, what they do is you either get this value, multiply it by 10 to the 3, and then that's the value you're supposed to use for the specific volume. For example, B sub F at 10 degrees C for water. Is it 1.0004 or is it 1.0004 times 10 to the minus 3, or is it 1.0004 times 10 to the plus 3. Answer A, answer B, or answer C. Last clicker question. And I didn't put the units in there, but the units are meter cubed per kilogram. So I want to know specific volume of water, saturated liquid at 10 degrees C. Is it answer A or answer B or answer C? That was a low question, Professor. Here's a one to help you. Are these two numbers the same? Are those two numbers the same when it's critical point at the critical point? Are they supposed to be the same? Yeah. So how do you get this number to be the same as that number? This column has no 10 to the plus 3 or anything like that. What do you have to do to this number when you grab it out of the table? You have to multiply by 10 to the minus 3. 10 to the minus 3, right? So guess what the correct answer was? Yeah, that's why I think I'm no good. I asked a tough question. It is B. All right, let's do this again. Think about this is with your hands, the volume occupied by 1 kilogram. When it's liquid, it's small. So this number right here is 0.001004 meter cubed per kilogram. And then when it goes to saturated vapor, it's like 106 meter cubed per kilogram. Huge increase at 10 degrees C. You can see the numbers that I used earlier. This is 0.00100435 meters cubed per kilogram saturated liquid specific volume, and then it goes up. Last thing I'll comment on, there's a 0 in the table. And whenever you have energy measurements, you got to set the datum point somewhere. You have to start your energy measurement somewhere. For water, they said, why don't we put the specific internal energy at the, not the critical point, but at the triple point for the saturated liquid to be 0. And that's why it's right there. Another person could have picked a different datum point to start the energy measurements, but U sub F at the triple point is set to be 0, and that's the datum point. Thank you very much for your attention. If you need to check on your exam or anything, I'll be in my office promptly after this class.